This is session C7, 3 dimensions and spatial wrap-up. Last session, C6, we did particle in a box, part 3, superposition states. Today we'll finish our introduction of spatial problems. This will be the end of the C series of lectures. Let's extend particle in a box from 1 dimension to 3 dimensions. That's easy to do. Let's take interval 0 to A in the x-axis, 0 to B in the y-axis, 0 to C in the z-axis. It'll be an infinite well. The particle will never be present outside the box. It's just now we have a 3-dimensional box. It's not difficult to show that the time-independent wave function will be a function of x, y, and z, and we'll have 3 quantum numbers. And the normalized wave function will be square root of 8 over ABC sine n pi x over a, but in this case the n is specific to the x-axis, n sub x, times sine of n sub y, pi y over b, times sine of n sub z, pi z over c. That's the wave function inside the box. Anywhere outside the box, it's 0. And each of the 3 quantum numbers varies from 1 to infinity. The time-dependent wave function is just the time-independent wave function times e to the minus I e t over h bar, where e is a function of the 3 quantum numbers. E sub n sub x, n sub y, n sub z is pi squared h bar squared over 2m, mass m, times the quantity n sub x squared over a squared plus n sub y squared over b squared plus n sub z squared over c squared. An energy level might be non-degenerate or degenerate. Let's take the special case of A equals B equals C. In that case, energy eigenvalue E sub 111 is non-degenerate. The only energy eigenfunction for it is psi sub 1, 1, 1. But if we take energy eigenvalue E211, that has the same value as E121 and E112. So that energy level is degenerate with 3 energy eigenfunctions: psi 211, psi 121, and psi 112. That's all we're going to cover for particle in a box in 3 dimensions. This is a possible time to take a break. Now let's look at particle in an infinite spherical well. 3 dimensions, but instead of Cartesian coordinates, we're going to use spherical coordinates. There'll be radial distance r from the center of the spherical well. There's a potential that's a function of r. It'll be 0 inside the sphere, r less than capital R, and it'll be infinite outside the sphere, r greater than capital R. We're only going to look at the ground state. There will be no angular dependence. So this is relatively simple. The excited states have angular dependence and are complicated, and we're not going to look at them. So here's the normalized ground state time-independent wave function, psi gs for ground state. It's a function of radial distance r. It's a normalization constant, and then sine pi little r over big R divided by pi little r over big R. That's the wave function inside the sphere. outside the sphere, it's 0. And when r equals capital R, sine pi will be 0, so it will be 0 at the sphere. The time-dependent wave function is just the time-independent wave function times e to the minus e over e time over h bar. E in this case is the ground state energy. Easy to calculate if you know how to take your derivatives in spherical coordinates. The ground state energy is pi squared h bar squared over 2m capital R squared. We can, relatively easy with the Wolfram alpha, we can calculate the expected value of the radial distance. So expected value of R for the ground state. And we get that it's capital R over 2. Let's plot the wave function for the infinite spherical well. Here we're plotting the wave function times capital R to the 3 halves so that we can have a vertical axis with actual values. So it's this blue curve. It's square root of pi over 2 at the origin. It decreases with radius until it's 0 at the wall of the well, at the sphere. This ground state wave function has no nodes inside the well. The expected value of radial distance is capital R over 2, and I've plotted that point. Expected value of R. Now switching gears slightly, for the hydrogen atom ground state, the expectation value of R equals 3 halves times A0, the Bohr radius from the hydrogen atom. Let's take a special case for the infinite spherical well of capital R equals 3A0, such that we get the same expected value of R as for the hydrogen atom ground state. R equals 3A0. Expected value of radial distance is 3 halves A0. Now we can plug that value in and for the energy, and we get the ground state energy is pi squared h bar squared over 18 times mass times Bohr radius squared, and we can use the numerical values of these constants, and we get a ground state energy of plus 14.9 electron volts, where for the hydrogen atom ground state we had minus 13.6 electron volts. Now these are not equal, but they're certainly the same order of magnitude. We had two different potentials, but we created a case where the two cases had roughly comparable spatial confinement, and we got roughly comparable ground state energies. From Heisenberg's uncertainty principle, the minimum uncertainty in momentum is determined by the uncertainty in position, and from the momentum we can get a minimum kinetic energy and a minimum total energy. And so we can understand how roughly comparable spatial confinement could give us roughly comparable ground state energies. This is a possible time to take a break. New topic: tunneling through a barrier. In classical mechanics, a particle cannot cross a potential energy barrier higher than its energy. But in quantum mechanics, there's always some probability for crossing or tunneling through any finite potential barrier. Here's a drawing of an energy barrier. Energy 0 but we have this barrier and barrier energy V. It's finite width. We have a particle starting on the left, moving left to right. It has an energy E relative to the zero level, but that energy is less than the barrier height. Classically, the particle could never would bounce off the barrier. It would reflect off the barrier. It could not ever cross the barrier. But quantum mechanically, it can and does. We know that we will have a sinusoid we will have a free particle to the left of the barrier and a free particle to the right of the barrier, and they have the same energy, so they'll have the same wavelength on both sides of the barrier, but they need not have the same amplitude. And here is what, if we did the math, we would find that we can construct a wave function that is a free particle to the left of the barrier, a free particle to the right of the barrier, and within the barrier it has a wave function which is an exponential decay because the energy is less than the barrier energy. And we can match up the boundary conditions so that the wave function is continuous at both sides of the barrier, and the slope of the wave function is continuous at both sides of the barrier. The fact that the amplitude is higher on the left than the right, we can get the probability density from the amplitude. So we start out with a particle with some probability density on the left, and it will have some probability density on the right of going through the barrier. Now it will be that the relative probability densities will be a complicated function of the barrier height and the barrier width, and the barrier does not have to be flat, it doesn't have to be rectangular, but no matter what its shape and no matter what its finite height, there will be some probability of tunneling through a barrier. The probability could be pretty high for a barrier that's thin and not very high. But a high barrier that's wide, the tunneling probability could be very low, and in fact it could be 10 to the minus some large number. The probability of tunneling through the barrier could be so small as to be effectively zero, but not truly zero. We're not going to work out the details. I just want you to know the effect. Tunneling is used in certain electronic devices and some electrical effects, and it explains the half-lives of nuclear radioactive decay. This is a possible time to take a break. Angular momentum. The quantum mechanics of orbital angular momentum of two-dimensional and three-dimensional spatial systems is important, it's interesting, it's complicated, it's mysterious. I recommend the two MIT quantum mechanics courses 804X and 805X for a thorough treatment of it. I'm only going to give an introductory teaser here to motivate you to want to learn more. We can define an operator of orbital angular momentum in the z direction. Orbital angular momentum is L. Z direction is subscript z. It's an operator. I wrote equals, but it should really say defined as. This is defined as x times the y direction momentum minus y times the x direction momentum. This definition does not depend on any particular wave function. There's no presumption of orbits or any classical trajectories. So in any two-dimensional or three-dimensional problem, we can use the orbital angular momentum operator LZ. In three dimensions, we can also define operators L sub x and L sub y. And once we have them, we can define another operator, L squared, which is Lx squared plus Ly squared plus Lz squared. It seems funny that why would we do this, but actually it is not only useful, but it's needed. All four of these operators, Lx, Ly, Lz, and L squared, they're all four observables. They're all Hermitian operators. And so, in principle at least, any of the four operators can operate on a state to measure the state. Now, Lx, Ly, and Lz do not commute with one another because x does not commute with momentum p sub x, and y does not commute with momentum p sub y, and z does not commute with momentum p sub z. So Lx, Ly, and Lz do not commute with one another. So we cannot simultaneously measure any two of these generally. But Lx, Ly, and Lz do commute with L squared. We're not going to show that. And these all commute with a Hamiltonian for a central potential, dependent on radial distance but not angles to the axes. For a central potential, we can and do find energy eigenfunctions that are simultaneously eigenfunctions of L squared and Lz. But when we do that, they are not also eigenfunctions of Lx or Ly in a general state. The eigenvalues of Lz orbital angular momentum in the z direction turn out to be quantized in units of h bar, integer times h bar. Recall that the Bohr atom had orbital angular momentum quantized in units of h bar. The Bohr atom was incorrect in supposing that there were fixed circular orbits, but it was correct in that the orbital angular momentum is quantized in units of h bar. It also was correct in predicting the energy levels of the hydrogen atom and the general size of an atom, a hydrogen atom. The eigenvalues of L squared are quantized as certain integer multiples of h bar squared, but it's a little trickier and we are not going to go into that. Now, there's nothing really special about the z-axis. We could choose any direction and call it the z-axis. But once we do that, in spherical coordinates, the z-axis determines how we define the polar angle theta, and then the x-axis determines how we define the azimuthal angle phi. And so we commonly will use Lz. We will not commonly use Lx or Ly, but we could. Simultaneous eigenfunctions of the Hamiltonian, L squared, and Lz have interesting angular dependence. These solutions are called spherical harmonics. They also exist in classical mechanics. And these spherical harmonics give atoms their interestingly shaped p, d, and f orbitals, and molecules their sigma and pi bonding orbitals. There's much more to learn about orbital angular momentum that we will not cover in this class. This is a possible time to take a break. Intrinsic spin angular momentum. In addition to the orbital angular momentum associated with a spatial wave function, elementary particles and composite particles possess an internal property called intrinsic spin angular momentum, or just spin for short. This is real angular momentum, but it's separate from the spatial wave function, separate from orbital angular momentum, separate from the potential energy function. It's just an intrinsic part of that particle. This is the case even when the particle is point-like, such as the electron. So don't think of it as a little bit of orbital angular momentum inside the particle. It's not. It's just a special property of the particle that never goes away. It's always there. We will cover introductory aspects of intrinsic spin angular momentum in the D series of lectures. So I'm only going to introduce a couple aspects here. The component of intrinsic spin angular momentum along any given direction, for example the z direction, turns out to be quantized in units of h-bar over 2, with different values of quantization for different types of particles. Some particles have their spin quantized in units of h-bar over 2, and that is called spin 1/2. And that's true for electrons, all other leptons, neutrinos, protons, neutrons, individual quarks. Other particles have their spin quantized in units of h-bar, and those are called spin 1. That's true for photons, which mediate electromagnetic forces, gluons, which mediate the strong nuclear force, and the W and Z bosons, which mediate the weak interaction. Other particles are spin 0, spin 3/2, spin 2. We're not going to mention them. The total wave function for a state, for a non-relativistic particle, so we can use the Schrödinger equation, consists of a spatial component and a spin component. It might simply be the product, the tensor product of a spatial wave function and a spin wave function, or wave vector. Or it might be a linear combination of multiple such products. Particles with integral spin, some integer times h-bar, are called bosons. For example, photons are bosons. Particles with half-integral spin, and some odd integer times h-bar over 2, are called fermions. For example, electrons. Bosons are named after an Indian physicist, Bose. Fermions are named after an Italian then American physicist, Fermi. This is a possible time to take a break. Multiple particles and identical particles. The total wave function for a state for a system of 2 or more non-relativistic particles might simply be the product, the tensor product, of the wave functions of each particle individually, or it might be a linear combination of multiple such products. In the second case, the total wave function is more clearly for the system than for the particles individually. In particular, the spin state for a system of multiple particles may be a linear combination of tensor products of individual particle spin states. All electrons in the universe are identical to one another and indistinguishable from one another. We might label them 1, 2, 3 when we think about a problem and we're, writing its equations. But physically, they cannot be labeled or distinguished from one another. Likewise, all protons are indistinguishable. For each type of elementary particle or composite particle, individual particles are indistinguishable from one another. This means that sometimes a presumed wave function that we write could be not physically real because, we might have written a wave function in which we can distinguish between identical particles that are in proximity to one another. But that's not physically possible in the general case. So we can write wave functions that naively might seem correct. They might seem to, obey the Schrödinger equation, but they're not physical if the result allows us to distinguish between particles that are physically indistinguishable. So we would need to fix that. For a system of multiple non-relativistic particles in some proximity to one another, for the system total wave function to represent physical reality, it must be true that exchange of any two identical indistinguishable particles must cause the wave function, the total wave function, spatial plus spin, to remain unchanged if those two particles are bosons, called symmetric under exchange, and must negate its sign if those two particles are fermions, such as electrons, which are antisymmetric under exchange. That's what we need to do in order for the total wave function to represent physical reality for the indistinguishable particles. In both cases, the probability density remains unchanged for the exchange of any pair of indistinguishable particles. This gets complicated, but it is important and it has observable consequences. We will look at the physical spin states of two electrons in the D series of lectures, and we will also look at entangled states. This is a possible time to take a break. Pauli Exclusion Principle. Wolfgang Pauli's exclusion principle. Two or more fermions, for example electrons, in a system cannot be found in the same state, total state, spatial plus spin. It turns out this is a consequence of the quantum mechanical treatment for identical particles, that exchange of two indistinguishable fermions must negate the sign of the total wave function for the system. This is proven in the final chapter of MIT-X course 806X, the third course in MIT's undergraduate series on non-relativistic quantum mechanics. So it takes 3 semesters of relatively hard work for an MIT junior to get this far in physics, to get to the Pauli Exclusion Principle. But in chemistry, we're given without proof the Pauli Exclusion Principle immediately after we learn about atomic orbitals as a college freshman or sophomore, or even in a high school honors chemistry course. So in a chemistry course, you might hear, I probably could spell that correctly, you might hear the Pauli Exclusion Principle expressed differently. So instead of two or more cannot be found in the same state, it'll be expressed as at most 2 electrons can occupy a single atomic orbital. Well, is this the same thing? Is this different? Is it consistent?
The other one said you can't have two. This says you could have two, but you can have two, at most two electrons in a single atomic orbital, which is different than a quantum mechanical state. Expressed this way, it's implicit and unstated that there are two spin states for the spin 1/2 electrons for each atomic orbital spatial wave function. So, one electron in each total wave function state. So total wave function state, spatial plus spin. So those two statements of Pauli Exclusion Principle are consistent, but you need to know a little bit in order to not be confused. So when two electrons occupy a single atomic orbital, you will hear in books and classes they must have opposite spin. Well, it's a little more complicated than that because the electrons are indistinguishable. So actually, the pair of electrons is in a special entangled state called the singlet state, which is antisymmetric for exchange of the particles, and this allows the pair of electrons to occupy the same spatial wave function. The singlet state has zero total spin. We will look at this spin state in the D series of lectures. This is a possible time to take a break. Moving on, this is the end of our introductory treatment of spatial problems, though there's much more to learn. Congratulations on getting this far. The D series of lectures will be on spin states. If you're ready for more material on spatial problems, or you want more depth or more solid grounding, and you have some experience with calculus and differential equations, more than I've assumed and required in this course, I recommend that I recommend MIT's 3-semester online series of undergraduate non-relativistic quantum mechanics courses on edX. And those are 804X, then 805X, then 806X. Following, I'm going to show you the chapters in each course. And I'm doing this for two purposes. One, I want you to see that we have covered a lot of the topics, although we've only done so in an introductory form, and the MIT course will cover them in a thorough form. And the second, I want you to see that there are some topics we haven't covered that are covered in the MIT courses. So I'm not going to read these chapters, the chapter names, you can read them. But if you feel ready, I encourage you to take 804X and see how you do. And if you complete it and enjoy it, I encourage you to take 805X. And then there's 806X. Which ends with identical particles, a little bit of which we've covered today in the most introductory way possible. This is the end of lecture C7 and also the end of the C series of lectures on spatial problems. We won't be doing any further spatial problems in this course. If you want to go further, take the MIT course.